here we go. We are live, and we're gonna switch this camera back over. Woo! Yeah, I wouldn't expect anybody to be here now. We've done this for how many weeks, months?
6 weeks.
Yeah, people are busy, man. They can't be doing this. Like, we schedule our time here, but the videos are out there, and people can watch it that way, which I would expect. And today's an exciting day anyway, because we finally get to play with decentralized authentication. Now, the code that we're going to need for this, I wrote about 2 years ago when I was working on the blockchain project. So I don't have a full intimacy with it. We're going to have to go through all that code. So what we're going to do is write a little hack program that makes all the API calls we need for both the client and the server. Make sure that we know how to do it all, and then we'll integrate it back into the thing. Just same way I did it with the WebSockets, same way I did it with whatever is the last thing that we worked on. So you notice that with me. Write a little hack program, get all the APIs straight, then do the engineering. Don't try to do it all at once, because it's too hard. But I definitely want to do some whiteboarding first, so at least we have a general idea of what we're trying to accomplish.
Yeah.
Now, the people who wrote the math that makes this work are all on serious drugs. They're not sharing them with me, so I can't do the math. I'm not even going to try to explain the math. We're just going to understand the semantics of what the math is capable of doing.
Okay.
Okay? Yeah. So just understand that, dude. Okay? The math is way beyond my brain. In fact, there are people that work on cryptography every day that also don't understand the math. They don't need to. They need to understand how the APIs work and the security behind the APIs and the vulnerabilities behind the APIs. That's going to be us today. It's not about really understanding how the math makes all this magic. It's got to make sure we use it right. All right, I have a little Cuban coffee here. Ali made us some more Cuban coffee. We're going to be bouncing. It's my second cup today. It's okay. All right, I'm going to go into under chat. Excali draw. All right, we're gonna do some Excali drawing again today. Let's bring this up.
It's my favorite.
So let's talk about what we mean by decentralized. Well, first of all, when we talk about anything being decentralized, what we're saying is there's no central authority that owns that particular piece. So if we were to put Redis in or database in and host it, and every cap had to talk to it, now we've just centralized something. Now, we can make an argument already that NATS has created some centralization, at least the way we're using it, right? Because we're accessing this thing. We don't own NATS. Opsaria owns it. They could shut it down tomorrow and take our whole network. And so ideally, if we were going to really want to put this in production, we'd have to start sort of deploying NATS ourselves, right? And make it easy for anybody to deploy a NATS environment out on the public internet, right? Just like Ethereum allows you to bring down the Ethereum service, and you can run that locally. And if you have a public IP address, run it somewhere. So, sort of the same thing. We ain't going to try to solve that problem. We're going to pretend that there's a world of NATS things here. But if we want to do authentication, which means what? We want to authenticate that this person is allowed essentially on the system. Authentication doesn't describe what a person can do. That's authorization, okay? Authentication just describes that we know this person exists, all right? They're a valid, they're not even valid. They're a known person as it relates to this system.
Got it.
Okay, that's authentication. Authorization defines what they can and can't do. Now, we don't really have an authorization component to this system, because the only thing we do is we chat and we send files. And so once you're authenticated, once we know who you are, in a sense, then you're able to do whatever it is you want. We don't restrict anything, which is fine. In our case, though, the whole point of wanting authentication here is so nobody can steal your identity online. Right now, we randomly generated an ID, right? I can't remember what my number is, 53 something. You generated an ID. I have in my little contacts file, that's Kevin. But anybody on this thing could start to pretend that they're me.
Yeah.
That's not good, right?
No.
So what we need to do right now with authentication is create a way of really being able to define an identity that nobody else on the planet can spoof. That's really what we're looking to do here with this sort of authentication.
Mm-hmm.
It's not even really authentication when you think about it that way. This is more about identity management, but decentralized identity, okay? So how can we do that? Well, there is a protocol here that, or a cryptography that Ethereum uses called, I can't remember the name of it. Let's look it up. My brain just shut down. So I'm going to bring up the, did I not bring up the blockchain project? Let me bring it up. So it's like ECDSA, but I'm going to look it up real quick because I have in here stuff we're going to steal, by the way, but we'll understand it, I promise, before we're done. Oh, that's it. ECDSA. That's what I want to look up. So ECDSA, or elliptical curve digital signature algorithm, right, is the cryptography we're going to use to do this, essentially this decentralized identification is what we want. And every time you see something like this, you see these images with curves where a curve hits the y-axis 2 times, and you'll see values related to this as well, okay, as part of the data that this ECDSA sort of generates. So I'm going to talk about this stuff at a high level, but somebody figured out the math to all this craziness, okay? And so it's not important to understand the math. It's important to understand sort of how all this works, okay? And this is essentially what Ethereum uses to deal with the Web3 identity that it does, okay? So let's sort of, blockchain here. Let's sort of come back here. So here's the idea, right? We're going to have, we'll just keep it down to even a single cap right now, okay? So we have our cap, right? And even though right now we run a cap locally and we only have one client connected to it, ideally, any number of clients can connect to the same cap. We agree, right?
Yep.
We're not doing that because we're on separate machines and we're using, we're using NATs as some sort of fabric to connect these NATs caps together. But ideally, it doesn't really matter, right? We can talk about a single cap environment here. Now, what happened is I created some random number. You created some random number.
Yep. And
we use that number to identify who this person is and how to route messages. So if I want to send something to Kevin, right, and we say this in my database, Kevin is this ID.
Yep. And
in your database, this is Bill. Then you basically send a message over the cap to 123, and it magically shows up if I'm online, right? Okay. But we already said that, say Mohammed, who's been following us since the beginning, right, comes in and says, well, I want to be Bill too. And right now there's nothing stopping Mohammed from being Bill, right? So this is essentially we can call this the bad actor. Not that Mohammed's a bad actor, but you understand what I'm saying.
Yep.
Some bad actor here that can essentially be Bill. So this is what we're trying to prevent. We need a way of making sure that your ID is always unique to you, my ID is unique to him, and this bad actor can never pretend to be me or you.
Yeah.
All right. So what we're going to be doing is the following. Using this, what was it? You would think I could remember that. ECDSA. What we're going to do is create, what was that? Oh, shoot. I didn't even know that was there. We're going to create an ECDSA private key. All right. And with the private key, all right, we'll just call this private key PK. And with that private key, we're going to also have, essentially, anytime we have this private key thing, we can also
Public
get
key.
a corresponding public key. We can call that the pub key, okay? We're going to have these two things. Now, we can create these private keys in different ways. If you're doing an actual wallet on Web3, then you want to give it one of those 12 to 24 word key phrases and generate the private key that way. In case you lose your key file, you can always recreate your private key, because once you lose the ability to recreate that private key and you lose the private key file, you're done, son, because this is supposed to be secure. There's no way to get it back. Ideally, there should be no way to generate the same private key twice unless you use the same data.
Yeah.
Now, we're not going to do a pass code here. We're going to have an API in the ECDSA Go package that we're going to use, where we can tell just generate a private key for me and write it to disk. Now, that's a dangerous way of doing it because, again, there's no way to reproduce it, but it's the simplest key API that we have there. And when the client starts up, what we're going to do is look to see if there's a private key there, and if there isn't, we could just tell it create it, and that will be your basically your private key or your identity moving forward.
And it'll generate that private key that first time you start it up. After that, you'll always
it should see it, right?
Okay.
Same thing we did right now with the regular ID.
Yeah.
If somebody wanting to use this system wanted to get more sophisticated, then when the client came up and it didn't see it, it could ask for a passcode and
got it.
generate that private key, and then you can be the same everywhere instead of copying it around, right? So for our purposes, there's lots of ways to create this private key in a way where we can't reproduce it again, or it is definitely reproducible. So anytime you're doing Web3 wallet stuff, you wouldn't want to generate private keys like we're going to do. Yeah. You want the passcode, right? Okay. Now, we're going to have that private key file here in that czar folder. It's going to be there. Now, what's really cool is we're going to leverage a part of the public key, okay? A certain number of bytes related to the public key, which will represent your ID. So what we're going to say is the public key represents your identity. Remember, anybody can have the public key. You don't want to ever give anybody your private key, because then they can do things like you. But the public key, in our case, in this environment, is your identity. Now, it's not the entire public key. They take the public key and let's just say they shrink it down to a smaller sort of number, right? So if you were to, I might have this here in my art. Okay, so this is my ECDSA ID for Ethereum. That's what IDs are going to look like in the system. They're going to be basically this big, and they're going to be looking like this hexadecimal sort of numbering system, okay? And this number comes from the public key pair of my private key.
Got it.
Now, somebody built, so this is ETHScan. So you could see how long ago it was that I played with any of this stuff. But if I was going to tell somebody to send me money, this would be the address to look up. Now, somebody built, this would be a centralized system. They built like a DNS for these sort of identities. I forgot what it was called. It might be called, I forgot what it was called. But I think I registered might be a while. I think I registered myself one time in this DNS system. This is how long ago it was, bro. And it didn't come up. And none of this is like me here. I thought it was maybe that. But I don't remember if it's called EA. Instead of DNS, they called it like Ether. Let's see. Ether. Let's try this. Ethereum name service. There it is right there. ENS. They called it ENS. Okay. Now we're not going to use this. We could technically use this if we wanted to take it to a next level, right? And I registered a name here, and of course I can't remember, and I don't have a link to it anywhere here, and I totally can't remember what I linked it to, man. But if I could remember, and I swore it was going to be like, oh, maybe that's why, because I didn't do ETH or something there, but I shouldn't have had to. I don't remember what I called it, This might, is this it? Because this address looks much more familiar to me than the OD one, I swear, was mine, not that other one I showed you. This might be it right here. I wonder if we could look it up. So I think this is my public address. That O1D looks more familiar to me than what I saw 063. So this might have been something crazy I did one day. I don't know. Anyway, not to harp on this, but I wanted to show you this because I was just looking one more time for anything else there. So I think this is definitely my thing. So remember when I put wkennedy.eth, that did an ENS lookup on this system here that I registered my basically my public identity on here, and I was able to do that. And that was so long ago, I don't remember how to do it anymore. But ETHSCAN did that search against ENS, and this comes up. And so I really do think that's it. So at the end of the day, we're generating this. That's your identity, okay?
Got it.
That's what we're trying to get to. Okay. So you see I got like no money there. I got $38 in Ethereum right there. That's what I got.
Nice.
Okay. So that public key is going to represent your ID, and it's going to be a number that, let's just take this right here, that anybody is allowed to see, right? So in my case, on, say, Ethereum, I have a wallet with that stupid long ID there, right? I don't know if I can shrink it anymore, but there it is. So this is what I switched everything to a string, essentially. Now, there will be special Ethereum types related to this ID that we can use. So we can make sure we're type safe and not just a string. We'll get to that at some point.
Oh, okay.
Okay? But now everybody is going to end up with one of these silly long sort of numbers.
But they're not going to be sharing that between
This is. I'm going to have to give you mine, and you're going to have to give me yours in order for us to talk.
But it won't be that shortened version that you were talking
No, that's the short version, dude.
Oh my gosh.
That's the short version. Okay, that's your public identity right there. Okay, your address. Okay, is your public identity. That's why a system like ENS is nice, because what we could do if we do an ENS lookup is instead of using this ID, you would use wkennedy.eth, do an ENS lookup, and then you get back this. It's the same thing with IP addresses, right? Everybody has you don't remember the number, but there's a name resolution. Yep. ENS was for name resolution on these silly, fairly large numbers. And that's like still smaller than the public key, right?
Okay.
Right? But at that point, if we're going to use this, then I have to be able to recreate a private key file and we ain't doing any of that stuff. You can do it, right? But then we have to build some tooling to do it, and it's just it's not important. What's important right now is that's where we're heading at. Now, how does this actually work though between the CAP and the client? Because there's a couple things here. These clients can't be sharing their public key to the CAP. There's no efficiency in that, right? So in a traditional world, like if you were going to do encryption, what would happen is I would send you my public key, you would send me your public key, and then what I would do is take a message, encrypt it with your public key, send it to you, and you would use your private key to decrypt it. But for that to work, I need your public key. Right? That tends to be how all this stuff works. And when we do encryption, we're going to need that.
Got it.
But I'm trying to do identity right here. And so it wouldn't make any sense for Kevin, when he comes online, to send his public key to the CAP. Plus, you're talking to this CAP, but your message might have to go to other CAPs. And how are you going to propagate a public key across a distributed network like this? You can't. So we need a way for the CAP to be able to get your public key for every message you send.
Every time you send a message, it'll do that.
So ideally, the idea is that when Kevin sends a message to the CAP, here's your message, right? Whatever it is, this block of data, just consider the message a block of data. We need a way for the CAP reading this data to come up with, let's just say this is your ID for a long moment. What we need a way to do is when you generate this data and you send it, the cap can do some math and produce this ID.
Ooh, okay.
Right? Because if it can, then we know that nobody else can ever send a message that produces this ID. And it doesn't matter what the data is. In fact, the data always has to be different on every message you send, or somebody could figure out what's going on. So we're going to have to do a couple things here. If I break this up, your message is going to be in multiple parts. There's going to be the data itself that you're trying to send. That is the to, the from, the everything that we've got today.
Got it.
Okay?
Okay.
There's going to have to be what's called a nonce. And a nonce is a piece of data that you're only ever allowed to use once. A nonce is about just once. Now on Ethereum, what happens is when you create a wallet, it just starts at an integer with 1. And every time you send a transaction, it increases it. 2, 3, 4, 5. So every message that's sent has this nonce that has to change. Now, your wallet sort of tracks that. And Ethereum also has a way of knowing if you've used the same nonce sort of twice. But the nonce can be anything as long as it's always unique. So we could use a date time stamp for the nonce. Right?
Okay.
Right?
Yeah.
As long as it's always different. Because if it's not different, if there isn't some piece of data that isn't different, then somebody can spoof you with that data. Because what's going to happen is we're going to attach a signature. And this is where the ECDSA comes in. So we are essentially going to sign, maybe a better way to look at it is this. We're going to have the data, we're going to have the nonce, and then we're going to sign that. Okay? Sign these two pieces of information with our private key. That signature goes along the wire.
Got it. Okay.
So data, unique nonce every time, and a signature.
So because the nonce is unique, the data, like when you say data, we're talking the to and from messages. So like if I say hi to one person and then I say hi to another person, written the same way. Right.
The data would be the same.
The data would be the same.
That's right. We can't have that. We want to, right? Because then the signature would be the same.
Yeah.
See, for a given piece of data, your signature would always be the same.
Okay.
The way we're going to calculate the signature. What we want to make sure is that every piece of data you send over the wire, the signature is different.
The signature is different. Okay.
Because if the signature doesn't change, then people can start to hack on this thing.
So how do you avoid that?
The nonce.
The nonce is what makes
the nonce is what makes the data unique every time you send it.
Okay.
Without a nonce, all this stuff goes.
Yeah, because you could. That's where my mind was at. Because you could send the same data to 3 people when you're saying hi to everybody.
And you could still do that. That's fine. But the thing is, what you don't want is if there's some guy in the middle, right, or somebody's changed this cap and they're trying to figure out who you are because they want to spoof you.
Yeah.
Right. If anytime you send a piece of data, it's the same signature, then all they have to do is attach your signature to every piece of data, and now I'm you again.
Yeah.
So the thing is that this signature, the data that represents a signature, has to be different for every piece of data we send, and the only way to do that, guaranteed, is to add
the nonce.
Add a nonce. So when you look at things like Ethereum and Bitcoin, you always see that nonce field. Now, again, in Ethereum, it's just an integer. And the nonce in Ethereum also sort of tells you how many transactions you've sort of executed at that point. Now, I don't know if I can, it's been forever here, but I used to be able to see what the here it is, nonce.
Yeah.
Nonce 2. So this block, this transaction I'm looking at was the second transaction that I've sent, leveraging that that key in a sense. Okay.
Yeah.
That's the nonce here. But the nonce doesn't have to just be an integer. It just has to be a unique value you only ever use
one time.
So again, we can use a date time for our nonce,
Yeah.
and we're fine. But we get it down to like the milliseconds or something like that, right?
Yeah. Something.
Or we can use like Unix time, right? Some
Okay.
integer.
Yeah.
As long as it's different every single time, it's okay.
Got it.
So now here's what's cool. So Kevin, you've done this. On the client side, we have to do this. We have to generate for the data and a nonce. We're going to use our private key and some APIs they give us to generate this signature. The signature, as you're going to see, is in 3 parts. Okay? And we'll go through those parts when you see it. It's a 3-part signature. Then what's going to happen is this data is going to come over the wire and into the cap. Now, the cap is going to use another API from ECDSA that is going to be able to, leveraging this signature and this data, produce that value.
Okay.
Okay? And when it produces that value, then it knows that that's the person, that's the identity that sent it.
Got it.
Okay?
So we'll be, we're not giving the cap that value, it's going to
Calculate
It's
it.
going to basically calculate it on its own.
Yes.
And avoid all of that.
Yeah, I've got to make sure there's no bugs in it. So one thing that I do, which Ethereum doesn't, but what I do, because I'm always nervous about this stuff, is I add another piece of data to this. And I add the ID to it. So this is what I do. And this is what we're going to do. We're going to take the data. We're going to take your ID, and we're going to create a nonce.
Yep.
We're going to sign all of that. Then when the data comes in, the cap is going to pull the signature out, run an algorithm with this signature against this data. It's going to produce this ID, and then it's going to check, does that ID match this ID? As a second check. That way you're protected from an algorithm that's gone bad, right?
Yeah.
Because if we have a bug in this algorithm, it's going to produce an ID, but it may not be
the right one.
yours, and now somebody else's. That always gets me nervous. Ethereum doesn't do this, but I do it because I'm paranoid. So what you're going to do is not just sign it, you're also going to specify what the ID is supposed to be as an extra precaution.
Yeah.
Then the cap does all this. If the IDs match, then what we're saying is, okay, you're authenticated, and this message can be sent to the other side, right?
Got it.
And so data coming in, now, see, from my perspective, the client, for data coming in, I don't think we have to do this. I think we make it the cap's job to not allow messages to flow through the network unless they're
authenticated.
They're authenticated, right? Now, we could also decide that the client, once it gets a message, does the same thing as an extra validation, but I don't know if that's super important, right? Now, can somebody, this is open source, can somebody hack a cap? Yes, but can somebody hack a client? Yes, but, right, could you be spoofed that you think you're talking to Kevin and you're not? Well, guess what? When this message comes in, right, we're going to have the ID in there. I don't know if I want to, let's get this part working first.
Yeah.
But ideally, what we could do also is have the client also, we'll have the code here. It wouldn't hurt to have the client also do an extra signature ID, right? Because if somebody hacks a cap, they should still feel protected that if Kevin sent it using this ID, that I can also validate that. Now, one could argue that we don't even do it at the cap level, but I'd like to do it at the cap level, right?
Yeah.
Just because we don't have to flood the network with sort of bad messages, right? A bad actor.
Yeah.
So the question ends up becoming, do we want to also do the same thing here at the client level, or do we just say we trust the cap, that if the cap says that this came from Kevin, it came from Kevin. In other words, then messages coming in wouldn't need any of this.
Yeah, they would.
They wouldn't need it, right? And that's nice because that's a lot less bandwidth over the wire.
We're assuming the cap already did its checks and it's right.
Right.
And we're trusting it.
Right.
And
Now, decentralized, open source, people can do sort of bad things, but from cap to cap communication, we have to definitely do this. So when it goes to anytime the cap receives a message from either the client or another cap, we have to go do this. So this we will have to send over the NATS network.
Got it.
Okay? But I think what we could do is at the client level, just send the data as we do today, and it all works. And so you trust your cap. And nobody running this system would want to be spoofed. So why would you hack your cap to not do signature validation? It wouldn't make any sense, right?
Yeah.
And since most people are not connected to your hacked cap, they're running their own cap. As long as we're doing cap to cap, as long as we're moving all this data between caps and every cap is doing the signature, we don't have to do it at the client level. That's the beautiful part about the decentralization as well, right? You run your own cap. Nobody can hurt you unless you're hacking your own cap in a bad way.
Yeah.
Right? Like you could rewrite your cap to not do any signature verification, but why would you do that?
Yeah, you're only hurting yourself, basically.
Okay. So I want to write a hack program that essentially, given some random data, right? Well, first, generate the private key. Then, given some random data, knowing what your ID is, and using a nonce, we sign it. And then what we do is do the signing verification. Okay? So there's two parts, and then the data can come down here. So the first part is creating a signature.
Yeah.
The second part is
validating it.
It's not really validating it in the sense that we create your ID and then check against that ID. That's the validation part.
Yeah.
Okay? Now, if you really felt confident in your algorithm stuff, you wouldn't have to do the ID check. You would just say, this is what it is. When you're dealing with money, nobody wants to hack that because now the money didn't go in their wallet, per se, right? But still, it makes me nervous. I never understood why Ethereum didn't pass along the ID with this signed data just to like check that this is me, like really, really me. Because when I was first coding the blockchain, I had bugs here and I wasn't generating this number. And suddenly I was putting money in somebody else's wallet because, right, if that was a transaction that said send money from here to here and I was generating the wrong ID, let's say, you know what I'm saying?
Yeah, no.
So this is what we got to do. All the code we need to do this is in the blockchain project somewhere.
Somewhere.
So yeah, dude, if you look at the repo for blockchain, it's been like years, man. So we're going to have to go do this slowly, but that's why I want to write the hack program. Okay, you understand what we're trying to do now.
Yeah.
This is really more like identity
verification.
Right? Identity verification, leveraging private and public ECDSA keys. So we don't have to publish a public key all over the network.
Exactly.
Yeah. Now, when we decide to do encryption, we will have to send, Bill will have to send the public key, Kevin will have to send the public key, because the encryption is going to happen, right? Encryption and right? Because you encrypt, data stays encrypted, and then, but this will be for, that gets interesting too. We'll have to figure that out because this data, this initial data can't be, encryption then is going to get interesting with identification later on. Now that I'm thinking about it. We'll figure it out, dude.
Yeah.
But you can see sort of where, okay, so excited?
Yes.
Yeah.
I've been hearing a lot about Web3.
Yeah, and a lot of smarter people than me have figured all this out. All right, so let's just start with our regular run function. All right, and let's do the if error run. I don't hate panic. I don't know why that is any sort of pattern. We could just do a log fatal, you know?
The R and return.
Yeah, that's fine. We're good. Okay. It would also help if I spelled return right. So we're going to hack in here. The first thing that we need to do, in fact, I'm going to write a separate function for this anyway, because we only need to do this one, okay? So generate private key. We can't do anything without the private key being generated, right?
Yeah.
All right. So let's just at least write this right now. and find the code that we need for that in the blockchain project. Now, my guess here is in the project, I have tooling. See, I built my own Chrome wallet too in this project, dude.
Ooh.
Okay, I have a CLI tool, I have tooling. Okay, so generate, here's generate. Okay, so we're gonna be using the Ethereum Go packages for this stuff, all right? And you can see here that there's a crypto package that says generate key. So I'm gonna steal this code for a second. This is the fastest way to do it. It's not the best way to do it because since we're just asking it to generate a key without any metadata, you can't reproduce this key. Like,
Got it, yeah.
never, ever, never, ever, never, ever use this key on Ethereum, because if you lose this file that we're gonna write,
Yeah, you're done.
you lost all your money, dude. And it's like it's gone. There are other APIs that will let you use a mnemonic to do this. But for our purposes right now, we don't need to do that. Okay. Get private key path. Where did I add that here to the root here? But that's fine. I don't know why I made that more difficult than I needed to. But we definitely wanted to add an extension to this. So let's do the following then. Oh, that's the blockchain set. Let's come here. Let me do a make tidy to start.
So we're still gonna generate we'll still have a file locally.
We're going to have an ECDSA, right? We're going to have a private key file locally that we'll create the very first time when the system starts for this system. If you ever lose that, then you would have to, it's just like if you lost your phone number, you have to go get a new number. You got to tell all your friends what your new number is.
Got it.
No different, really, right? There's no way to reproduce a phone number once it's taken from you. That's kind of how we're setting this up.
Got it.
Now, we do need a path for the file, right? So we can, again, how have we been figuring out where to locate stuff, right? We did it here using join, ID path, all that stuff. So why don't I do this? Remember, this is our hat, so I can hard code some stuff here. And we're running it from the root. So we know that it's going to be zarf. And right now, we've been just putting everything sort of at the root here, right? Which again has been bothering me because I like to be better organized. So I said this is when we would start to do some stuff here, right? So what if I created a cap folder and moved that in there?
Which we
won't
have that anymore, that cap ID.
We will. The cap ID has nothing. The cap is the unique cap that.
Oh, okay. I got it confused
fine.
with config.
Yeah. What I'm just going to have to do now on this version here is say that the ID file path is now under cap, right? Okay. So I'm going to put the cap ID under everything cap here. Everything client will come under here. Okay. And then for our front end, come back here. The config path is going to be under client, right?
Yeah.
Okay. Now the contacts too are going to be under that, and we just have to triple check that because I don't know how we did that.
I think I have just seen it. I've done new contacts config file path. File path.
Yeah. So it's perfect. So now, and so anybody on the stream you'll have to do this too. You'll have to move that stuff over. But now what we can do is say that your private key will be under zarf client. Let's just call it key. And then we can call it what did I do? Called it here. Well, I use that extension really. Yeah. So culture ID. What do you want to call it?
I like key better.
Okay.
I like key.
Okay. So this little piece of code will got to return the error. You know me too, right?
Yep.
Even you saw the one time I didn't do the error, and where was it failing?
And it bit us. Yeah,
Right.
it was failing right there.
Yeah. So, and I just, as a quick thing, I always just say like generate key, you know,
Mm-hmm.
as the wrapper. And then this will be, and you know, errors need to be at least start out lowercase. So, you know, that's fine. Like, you mean, you know, that could be whatever you do. Just try to find consistency in it.
Exactly.
All right. So this generate key would be cool. Now, one thing we could do also, if I go back to not this main, our services main. What we could do is this, right? Just in our hack. So if I generate the file name first, and if that equals nil, right?
Mm-hmm.
So if this doesn't return an error, we know the file exists,
Yeah.
and we shouldn't have to do anything else, right?
Yeah.
And so that means now that under run, we can sort of do a generate private key. And then if error,
Yep.
error not equals nil, generate private key is fine, blah, 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 blah. So we should even be able to run this now, right?
And it should generate the private key.
Yeah. So I already have hack here, don't I? Yep. Yeah, because I had it there and then I deleted it because we didn't need it.
Okay. Yeah.
So now we have it again. So let's see what happens now. So that's not good. Okay, so, oh, that folder didn't exist already, did it?
No, it didn't.
So maybe what we do is get rid of the extra folder.
And just put it in client. Okay.
Yeah, because what's in client now?
Contacts and config. So
Yeah, so we just put the key there. What's the big deal?
it'll only be one file.
Okay, so
Generate private key, client key.
so why did this fail?
We don't have it making the directory.
But the directory already exists.
Because
Zarf
we're doing
client. So this was right.
Zarf client key is open.
Yeah, that's weird. Saves the private key to the given file with restrictive. The key data is saved as hex coded. So why would it say? That's weird. Oh, it's trying to do an open.
It's trying to open before creating it.
Where was that? Okay, let's see. What error? Oh, you know, the one place I didn't. Okay, let's go through this code again. Stat is trying to open the file. If it can open the file, oh, it shouldn't return an error. It should just say nil. It's really what should happen, right? It can open the file.
But it needs to create. It needs to try to create the file.
Well, if it's not there,
If it can't open.
if that was a failure, then it should move down here, right? That's what I'm saying. So save. So we're seeing the error here. And the error is no such file or directory. So I am super utterly, let's go back to the blockchain code for generate. Oh, it just wants a path. Just wants a path. Doesn't want a file name, I don't think. See that? Let's go back and look at what the path is.
Get private key path.
Some concept of an account name and an extension. If it has this suffix, then, or if it doesn't have it, then account name plus key extension, join an account path and an account name. It's weird.
Which you're initializing above.
So let's just try this because I'm totally confused. Let's just do this for a minute.
And generate key is going to create that file that holds the key.
Ideally. Let's see. Like, out of all the things that I thought we'd be having troubles with, it's not calling save ECDSA. Okay. So it's telling me that we don't have a L, zarf. Line 29, yeah, maybe that's wrong and I'm reading it. Anytime there's fuzzy logic, there is a problem. Oh, dude, we're so silly, man. Oh, dude.
Oh, because it's because we're working inside of the chat.
Yeah, I'm not really working off of root.
No.
I mean, I am, but it's under chat.
It's under chat, exactly.
As soon as I tried to do this, I do this every time I use L. Like, list it, and it couldn't find zarf. And I'm like, of course it can't find zarf.
There it is.
Duh. Okay, so this is now our private key here. Okay, we can't lose this thing.
Yeah.
At least I can't lose it. This is going to now be my new sort of identity for everything that we do. Okay?
Got it.
Okay. So we now have it. So now if I run this again, it shouldn't change it, right? Let me see. 9C2, right? 9C2. Good. 9C. Okay. So this code is working. We just had the wrong path, didn't we?
Got it. Okay. Chat. Sorry.
So why don't we do this just to minimize our pain right now.
Put it in a const. Yep. We don't need that. File type.
Because we're going to be able to use this function, right?
Yeah.
At some level. Okay. So, okay, we now have the private key. Now, the next thing, all right, next thing we got to do is we got to be able to sign data. We got to deal with signatures and data. So, actually, the next thing I really need is I need to know what my public ID is.
Yeah. Public.
What is my public ID? Okay. So the next step is that. Now, I have a package here called signature.
Yeah.
That I put all of the sort of key stuff in. Like you see a sign, right?
Uses a specified.
Right. Well, don't worry about all the code just yet. But I have a sign function.
Okay.
I got a verify signature function, which I'm not sure we can use. The from address. This is the big one. Okay. So given a piece of data, and I told you the signature's the signature can be in two different forms, depending on how we're dealing with it. The signature can be in this form, which is a VRS form, and R and S have to do with certain points on the curve, and the V, I can't remember what the V has to do with. But the from address is what we're going to need, given the data and this signature. Okay, it will sort of go through these crypto APIs. Signature to pub. Okay, public to address, which is the ID we want. So I have a feeling, though, that if I come back here, I want to have the private key. Now, there should be a function I can use to at least read the private key off of disk, right? So if there's a save, I wonder if there's I need to be able to read this private key. So, and I'm sure I've got code there that's doing it. I just thought I'd find it really quickly here. Okay, so let's go back here to the tooling here. Because I have to be able to read the load. There it is, load. Okay, let me just do this for now.
So that's gonna get it from. Okay, yeah, from that file.
Let's do it this way. There's your file name. And then this is your file name, right? That gives me the private key, just for now. Again, we're hacking, right? We're trying to figure out all the APIs.
Just getting it working.
Yeah. Load ECDSA. Okay. See, the private key always gives you the public key pair.
Mm-hmm.
Like, that's how all of these things work. And if I go back to signature, what I need is, what I'm looking for right now is, given the public key that I have, okay, what is my common address? And this is it right here. Okay, so, and we can't use this in the cap because I won't have the actual public key. Okay.
Got it. Yeah.
But that's the private key. I need the public key, but I need its address. I thought I needed its address. No, it just wants that. Okay. And this function here, given a public key, will give us the common address. Okay. So in our case, this is your ID.
Okay, so that got it. Okay.
All right.
So that's loading your private key and then giving you your address.
Now the ID is, we'll do it in hex. Let's see. Well, if I do this for a second, my ID is in the form of a common address. Remember I said there's a type that we could use?
Yeah, there's a specific type.
So a common address is this type, and let's just use string for a minute. Now, I don't know what it keeps complaining about. Print line, oh, I need an F, that's why. Okay, so let's just run that and see what the ID looks like. We may have to attach our own.
So this is getting your private key and then getting your public key from that and then turning the public key to an ID.
Okay, this is reading the private key off of disk, which already gives you the public key pair. All these systems do that.
It comes at the same time.
Yeah, well, with the private key, you can always generate a public key. So anytime you load your private key, there's always, in all of these cryptography packages in Go, the private key type always has a public key field.
Got it. Okay.
Whether you're using RSA or this or anything else. So we get it. Now, remember, on the cap side, we're not going to have the public key. We're going to have to get this ID differently.
Yeah, we'll get it from the signature.
Signature and all that shit.
Yeah.
Okay. But right now, you can see here that that's my public, that's my ID now, based on that private key. Okay. That's what everything's we should see this over and over again if everything's sort of working.
Got it.
Okay. So that's my new number. That's my identity. Okay. So that's the public key. Now, the next step is we need to be able to sign data.
It. Yep.
Now, we always sign data with the private key. Okay. We have that. So let's go find the code we need. So far, so good with everything, right? Okay. So I have this big function here that uses the private key to sign data. Now, let's talk about, we don't need a stamp. So when it comes to this cryptography work, you might hear the word salting.
Salting, okay.
So what salting is, or adding a salt, is taking the data and then hard coding or putting in the data some hard coded value, almost like your own stamp.
Got
to
it.
say that, you know, Kevin stamped this.
Got it.
Now, the stamp itself, when it comes to Ethereum, they have a stamp. It's not called Ardan signed message. It's called Ethereum signed message, right? And the way they do it is they have this hex value that says the number of bytes related to the salt, or we'll just call it a stamp. So in order for me, remember this code is trying to mimic Ethereum and Bitcoin, whichever one was easier.
Yeah.
I steal some things from Bitcoin, like the Merkle trees. They used a simpler version of Merkle trees. Here, all this stuff I used from Ethereum because their packages were already written in Go.
Okay.
So
it was.
So they
easy conversion.
stamp everything that they sign.
And the stamp is always the same.
Yeah, the
It's
point
always
is
the
that
same.
it's the same. So
Yeah.
when you look at the data, because it's not encrypted,
Mm-hmm.
remember the data is not, this isn't data that's encrypted right now,
Yeah.
but you can look at the data and see that it was, so it's not a private thing. Everybody can see that this was stamped by Ethereum. And the idea is that different blockchains use their own sort of stamp as a way of just saying, like,
this is from me. Yeah.
Yeah.
This is
But-
who did it.
it's data that goes along with all the data that's being sort of signed. Okay.
Got it.
Now, we don't need to worry about sort of stamps. Okay. I don't think we need to worry about it. But the idea here is given a value, if you look at the blockchain, what did I do? We're going to do something similar. Given the value, I convert it to JSON.
Mm-hmm.
Then I take this message and I create basically a slice of bytes with that signature. Again, 19 would represent, however the format is there. Okay.
Yeah.
So, and the length is the number of bytes. So one of the things that this block does is it says, okay, got 19 bytes for the signature, and then the number of bytes that are coming after. Okay. And then on the Ethereum side, they use this function, okay, which essentially takes this data
Yep.
and this data and it hashes it
Right.
at a fixed length sort of hash.
Got it.
So you
Okay.
take these two things and you end up with this sort of stamp. And then with the stamp, that's the data then that is I'll talk about that in a second. That's the data that we basically sign
Okay.
because they're now what I'm looking for is stamp returns the hash of 32 bytes that represents this data with the Ardan stamp embedded in the final hash. So this isn't the data itself, right? This is a hash of the data and the stamp. Just again, to keep things sort of unique with what's going on.
So it's including the data that we're sending with it, or it's just the stamp itself.
It's a hash of the data and the stamp.
The hash. Okay.
Okay. And remember, hashes are supposed to be unique.
Yeah.
And so what's happening here on the signing is that, at least on the Ethereum side here, we're taking this data,
Mm-hmm.
which is essentially the data itself and this stamp.
Yeah.
We're creating a hash of that. And then it's that hash that we're signing with the private key.
Got it.
Okay. And we could do the same thing. You could sign any aspect of that, right? And the hash is nice because it's just a smaller amount of data that you have to hash, right? Because you can have a large amount of data,
Mm-hmm.
but if you only have to hash this much data, the hashing algorithm is going to be what?
It's a lot faster.
Okay, a lot faster. So we could do the same thing, right?
Yeah.
Because some of these, in Ethereum, some of these blocks are like huge, right? With transactions.
Mm-hmm.
So it's faster to just sort of hash that and create a signature around that.
Got it. Okay.
So
I see.
then what this is doing is getting the public key.
Mm-hmm.
Then from the private key public, that returns public key. We take that and, that's a crypto. ECDSA, let's see. Oh, you can see that the public key is returned as a crypto.
Yeah.
Dot public key.
Public key.
So this here, what it does is it's asking, is the concrete value also implement the ECDSA public key? It does.
Mm-hmm.
So now we've got an ECDSA public key. and then we say on the crypto API from ECDSA pub,
Yeah.
using the public key, we get back this set of bytes.
Yeah.
This converts to okay, remember I told you this key is in two different forms?
Mm-hmm.
You can get it in the form of a slice of bytes, which is what we're doing here. So this is the conversion of the public key to a slice of bytes.
Yeah.
I don't know why, but some of the APIs that we use want the public key as a slice of bytes, and some of them want it in this VRS.
Yeah, the 3-part.
Right. So you can see that crypto verify signature wants the public key in the slice of byte format. Now, what this is doing is it checks that the public key created signatures of public key should be compressed to 33 bytes, or uncompressed 65 bytes. Signature should be 64. So the first 64 bytes is R and S, and then the last byte, which is the 65th byte, is this V. It's a 1 or a 0. And it all has to do with where things are fitting on the damn curve. And based on the V, the algorithm can be more efficient because it knows whether to use. So this is my highest level understanding. The signature has an R value and an S value.
Yep.
And the V value tells the algorithm whether to use R or S. And R and S represents at some levels, some points on that curve.
Yeah.
The V value can either be 0 or 1, meaning use R or use S.
Yeah.
Outside of that, dude, I don't know.
Got it.
But all I know is that some APIs want this public key in a set of bytes, and others want it in the VRS. Now, on this blockchain, I sent everything over as VRS. Because on the other side, this is what we sort of needed. So if I go to two signature values, this takes that slice of 65 bytes.
Yep.
The first
32, it's putting into
R. The next is S. And then this is a 1 or a 0. Now, another thing that Ethereum did on these signatures is instead of that being 0 or 1, they added a special integer value. It's called the Ethereum ID. Now, if you look at the Ardan ID, it's 29.
Yep.
So that means in this case, V can either be 29 or 30. Ethereum uses 27.
So it could be 27 or 28.
But in order to use the algorithm, you have to subtract that and get it back to 0 or 1. So these are all the little things Ethereum did to also know that this came from sort of them. Not that all this is private, it's all public sort of stuff. But so when I want to use the JavaScript Ethereum packages, I have to follow the Ethereum rules because I can't rewrite all that JavaScript code, dude. So one of the things you'll see in here is the Ethereum JS.
Yep.
You see these notes up here? I changed 27 to 29 and 28 to 30. And I had to change that all inside the JavaScript code. Because it was, and anywhere I saw Ethereum signed message, I changed it to what?
Ardan.
Okay.
So you could have used the Ethereum ones.
I could have, but I thought it
But
would
you
be
wanted
fun to have a unique.
To do it yourself. Okay.
But then when I went to the JavaScript and I was like, I can't rewrite this. Oh shit, this JavaScript is wanting to talk to Ethereum directly. I had to make those changes.
Okay.
All right.
So you made the changes in that specific.
Oh, I know. So if I ever get a new version of this Ethereum, right, I have to go back and change all this. That's why I left these notes.
Got it.
And I've got to get the version of this that isn't compressed so I can find it because these changes aren't in just one place.
Okay.
Okay. Interesting, right?
Yeah.
Now, we don't have to worry about this because I'm not going to try to do this in JavaScript. If I was going to try to do this in JavaScript, then we should keep this. Maybe we should keep all this. So if we wanted to do a JavaScript version, this JavaScript API would work for us, right? But again, we just got to make these sort of changes. So if I come back here, this is how we take the slice and break it into the VRS.
Yeah. So there
Right.
we're sectioning it off.
And we can use our Ardan ID too there, right?
Mm-hmm.
That's fine. Like we could use all this stuff. And that way, if we did want to go back and do a JavaScript version, that JavaScript package would let us talk to the cap essentially
Yeah.
appropriately, right? Again, you would pop-up JS has that, like, this isn't going to be our data, but you can see that the data has the nonce. It's going to be similar. We
Got
would
it.
just have to rewrite this. But we know the packages would work because we're doing all the Ethereum crypto stuff right.
Mm-hmm.
Right? So maybe we should just keep it. So now if that's the case, right? Let's just do this for a second. Let's copy our signature package into Foundation for a second, right? I mean, if this is going to be the case, right? Like if we keep this here, then we could definitely write JavaScript later on. Then we keep our Ardan ID the way we did, right? We have the ability to hash. We have the ability to sign. We saw now what signing means.
Yeah.
Is we take our data, we stamp it with our Ardan signature, we create a hash of that, right?
Yep.
Then we sign the hash with our private key.
Mm-hmm.
Then we go ahead here and check that the public key validates data and signature. We're doing our own verification to make sure our stuff isn't broken here.
Yep.
Okay, so we do our own stuff. And then we return the signature in this VRS format, because that's how we'll send it over the wire, because the cap side really needs it like that. Not that we couldn't just send the bytes over either, but I don't know why. I did it this way because that's what Ethereum does.
Yeah.
If you start to explore Ethereum, it's sending signatures, not as the slice of bytes, but in the VRS sort of format. So I just followed what they did, okay?
Got it.
So that's our signing. Now, you can only verify a signature. Okay, so this function verifies the signature conforms to our standards. So what does that mean? So the cap will do this. So when the cap gets the signature, it's going to get it in its VRS format. The first thing we do is we subtract our Ardan ID from the V value,
Yep.
right? If it's not 0 or 1,
Then we know it's messed
they
up.
didn't, right? They're not using our protocol,
Yeah.
right? And then we say validate signature. We give it VR and S, and this Homestead is a very old version of Ethereum, so I just say
Okay.
false, and it verifies that the signature validates our value within a given set of chain rules, right?
Mm-hmm.
Again, V needing to be either 0 or 1. So
Got
we have to do that sort of subtraction there, right? The from address. So given the data
Mm-hmm.
that that we signed
Yep.
and the signature itself,
Yep.
we stamp it again.
Mm-hmm.
Okay, so actually, given the data the original data that we started with,
Okay.
we stamp it again. We get the signature from that, right? Because remember, this is the data and the stamp hashed together. Then we get the signature back from the data. And then what we do is we return the public key that created the given signature. So then what we're saying is, based on this data and this signature, give me back the public key.
So this is us basically unraveling it.
This is unraveling it.
Okay.
So this data is going to be like the to and the from and all that.
The
So
message
we add our
itself.
stamp, we hash it, we basically take the signature we passed in and convert it back to the slice of bytes. Because this API doesn't work with VRS, it works with a slice of bytes. Again, I don't know why, but that's how it's
So
crazy.
it's a lot of conversion.
It's almost like the crypto, maybe it's the first time I'm seeing it. Maybe the crypto APIs work with the slice and the ECD ones work with the VRS, and I never noticed that till just now. So since we've got to use the crypto API, it wants the slice, right? So then given this data and this signature in the slice form,
Yeah.
we get back the public key, and then you already saw this.
Yeah.
And then we'll double check that matches. Right?
Okay. Yeah. Yeah.
And then this just returns a string version in a hex format of any given signature. So we can sort of display it like this, 0x. And to VRS from hex signature. So this, given a signature string, which my guess is this. So given a string that looks like this,
Yeah.
okay, it can convert it to a VRS format.
Got it. Okay.
Decode string essentially takes out the 0x in the front.
Oh, okay.
That's kind of, well, this is taking out the 0x,
Yeah. because
and then
it's-
we're decoding it to a slice of bytes, essentially, hex decoding. So that way we can then take the different parts out. Remember RSV.
Yep.
And then this, given a signature in VRS format, gives it back in the slice of bytes, but it also removes the Ardan. So it puts the V value back to 0 or 1.
Got it.
Remember, because anytime we work with the crypto algorithms, that has to be 0 or
0 or
1.
1.
But when we send things over the wire and we do things, we'll do it with the Ardan ID, right?
Yes.
So we can validate. And then this converts RS into a slice of bytes, keeping the Ardan ID
Got it.
for the cases where we needed that. Okay. So, and then everything else is here. So you now have an understanding a little bit of how we're going to do this. And we're keeping true to the Ethereum rules of taking the data, adding it. Let's go back to that one last piece here, because this is the big thing. So taking the data,
Yep. Stamping.
we convert it, in our case, to JSON,
Yep.
because this will be some Go struct.
Yep.
All right. We then create a slice of bytes. This is our, now if you notice here, it's saying there's a better way to do that. This is some new function that they added. I don't know why they want me to use it.
According to formula to the byte slice.
Yeah, but you're passing nil, you know, so I don't know why the linter feels like this is better than this, right? Because this is just a conversion of bytes to this. Whatever, it's going to work. So now we have the JSON. We have a stamp,
Yep.
right? Which is based on the number of bytes. You see how that's nice? It isn't necessarily completely fixed because it also determines based on the length of the data.
That you're sending.
And then we hash that into a value that we will end up signing. So this function, what it does is, you see, it takes a collection of bytes.
Yep.
And so it calculates and returns this KECCA K256 hash of the input. So it joins these 2 bytes of data and then generates the hash.
Got it.
But it's a fixed length hash, right? Again, all of this is it makes it really hard for anybody to sort of break through what's going on.
Because it's gonna be unique every time.
Yeah, and so when we sign something, we go through the stamp, and when we are doing the from, right, which is on the cap side, we go through the stamp, and we do everything sort of the same way. And like I said, if we go back to that JavaScript thing that Ethereum does, they're doing the same exact
that's what they
sort
do.
of thing, right? So we're just basically mimicking Ethereum, but using our own stamp values and our own
Got it.
salt. So you can call this a salt if you ever see that again. All right. So now, how do we use this package a little bit better now to get to where we want to get to? I want to sign the data, right? So to sign the data, then we need to use this sign function. Okay. So let's go ahead, and the nonce will be in the actual data now. So you'll see the nonce sort of right now. Where's our hack? Okay. So let's create some data. Now, what is the data that we've been playing with? Where is that? SDK chat. So what is the data? Let's go to the client for a second. Front end. What is the data that we send to the this,
ID and
an
message.
in message, right?
To ID and message.
All right, so let's take this for a second. Because right now that's the data that we send to the cap, okay?
Got it.
All right, so this is call it the data that we're gonna send to the cap. Yeah, and it's complaining because of that for a second. Let me just do this for a second just to get it over it. Now, this is the data, okay?
Yeah.
Now, I said there's two things that I want to add to this data to make sure that we can do everything that I want to do. One is we'll call it the from ID, okay?
Mm-hmm.
So if I add from ID to this, now the from ID is this common address dot string, right? It's the same thing we saw here.
Yeah.
So we do that, okay? Again, I want to use that to check that we got the right signature when we're done.
This is that part of the diagram where we're sending data, ID,
Yes.
and okay.
Now, we also need to send, in this case, the nonce.
Yes.
Okay, the nonce again could be anything. Now, what we could do, if I look at time package, the time package has a Unix,
Unix D.
like even Unix micro, which is an Int64, right? So, oh, but I want it the other way around. Dot Unix. I want it to give me the Unix time. How do I do that? Oh, maybe if I do now, I can get it. So time now. Oh, that's it.
Okay.
Yeah.
Yeah.
Right? So in our case, let's just say the nonce could be that. Okay?
We'll type Int64. Okay.
And that's a Int64. And so now every time we construct this data,
Yep.
this will be different every single time. That's our nonce, okay? And this should be good enough for what we're doing. It's down to the nanosecond, so it's a
that's
fairly good number. Even if you're like pounding it, we should never get the same one. So here's the data that we want to assign. We're going to add our from, we're going to add our nonce. Now, we have our signature API now, and we're going to have our sign. So the sign is any value. That's the data. And the private key is this private key, which we will have here on the client side anyway.
got it.
And then this is going to return our VRS and/or an error. It's one of the few times where I've got a lot of things coming out, right? And if there's an error,
Normally we wouldn't want to be returning.
normally you
things.
wouldn't do that, but for this, I think it worked, and I kept the ID the way it was.
It makes sense.
Okay, so there's our sign. Now we have a VRS, okay, and it's in our Ardan sort of format too, right?
Yep.
In fact, we can func.println VRS, and these are big ints, so I don't know how that ends up. Probably uses the stringer, so we'll see what it looks like, and then we'll play with the formatting. And it uses this big int form because they're big integers. So that's the signing, okay?
Yep.
Now, when we send this over the wire now, we will also be sending this data and VRS,
Yes.
okay? So that's the data, and now we attach the signature. And now we're on the cap side. So the cap side is going to use our from address. So given the data,
Yep.
okay, and given the V,
The R.
the R, and the S, okay, and we'll need functions when we write VRNS to pull it back into a big int and all that. We've got all the code for that. Okay, but given that, now we get the ID and/or an error, Okay. And now we do the same thing we did here. Print. So let's call this ID2. I'm not going to call it ID there, though. We'll call it ID2, right? And now we'll match the two.
Because this is the
Oh,
one,
it's already
once
a
it
string.
unravels it, once the cap side unravels it, that's the ID we're getting.
Right,
here
so this
from
is the
address.
cap side, right?
And above there, we were signing it.
Right, so let's just call this the cap side,
Yeah.
right? Yeah, I think you got it. All of this is the
Client.
this is the client side, right?
Yep.
Okay. You put an extra in here. So let's see what happens. If these two strings match, right?
Yeah, then we know
Then we have what we need.
which it looks like they do.
How cool is that?
That is pretty cool.
That's crazy, isn't it?
It's a lot of, and then there's
So ID, that was the signature.
V29.
Now watch this. Because of the nonce, if I run it again, what do you notice?
V is going up.
The
Well-
signature changed, but the IDs stay the same. The signature changes because the data changes. That is the key to everything.
Oh, okay.
That even though
Okay.
the data is changing, right? The signatures change with that data. You only get back to the same ID if you use the exact data bit to bit with the exact signature bit to bit.
Got it. Okay. Yeah.
That's how this all works. This is how all Ethereum, everything works. So I'm able now to know who you are based on the data you sent me and that signature that you sent me. You signed it. And it doesn't matter what data you sign. You can see it's changing.
Yeah.
I can always get back to your public key, essentially, your identity.
Okay.
The only reason I'm asking you to send the from is so we can do a second level check on that it matches.
And it's the nonce that's essentially making all that possible.
Without the
Because it's
nonce,
that's what makes it unique.
without the nonce, somebody can spoof you.
Mm-hmm.
Somebody can spoof you.
Very cool.
Because at some point, they could probably write an algorithm to figure out who you are,
Mm-hmm.
right? So you need the nonce. You can't be sending this. If it's always the same signature, then I can spoof the data. I can send any data I want and this signature that I found, and now I'm you.
Basically,
understand?
Yeah. Yeah.
So you might say, well, Bill, I'm always changing the data. Maybe not. Maybe the data is you sending $100 to Kathy,
Yeah.
and you do that every week. So the
Yeah.
data is what?
Exactly.
It's the same every time. So now you cut a deal with Kathy. You say, Kathy, I'm going to send you all of Kevin's money and we're going to split it 50-50. Kathy says, okay. The money's going to Kathy,
Yeah.
right? I can't change that because at least the signature is attached to that sort of data.
Yeah.
But I can spoof the system and send Kathy everything. The better trick would be to play the long game. Hey, Kevin, send me $20. Right?
Yeah.
And now I just go 100,000 transactions through the system before you know it. Right?
Wow.
Because I have your signature.
Yeah.
Yeah.
Well, that's cool stuff.
But what Ethereum does is it always makes sure that that somebody can't use the same nonce.
Yeah.
Because it has essentially in a sense, a database that knows, like, you've already used that nonce. You can't use it again.
Okay. Got it. So no one can spoof
If
that
you try to
nonce.
use the same nonce, Ethereum will come back and say you've already used that nonce. And it executes transactions in nonce order, which is another reason why they just use integers. So if two transactions come in and one is nonce 3 and one is nonce 4, it has to execute 3 before 4.
Oh, okay. So like, there's no way to go ahead of it. Like, okay, the last nonce was 4. You can go and
It also
Send a
now is
message
waiting
with
for
5.
5. It won't do 6 until it comes in. So you start playing those games, you get in trouble. So like sometimes a transaction is stuck because you didn't want to give it enough fee or not enough gas. And you need to do another transaction, but you can't do 5 until 4, and 4 is stuck because no miner wants to pick it up because there's no incentive. So now you've got to go in and get rid of 4, and then you can send 4 again, and then you can do 5. Like,
Got it.
like when
Okay,
that stuff
yeah.
happens, it sucks because you only do 1, right? 4 has 5, and they track what that is. So even my blockchain tracks, right? There's a you come in here. I would have thought it was accounts or something. Yeah, account. You see account?
Yeah.
I keep
Nice.
track of this stuff, right? So I won't let you do that. Now, we're not going to have a database of that kind of stuff. Okay? We are going to do this sort of nonce thing here. The only thing somebody could potentially spoof at that point is the same message, right? So if somebody captured this with that nonce and your signature, then they can send the same message again twice.
Got it.
Now, we're not dealing with money here, okay? And if somebody wanted to say hello, Kevin, from me twice, go at
Yeah.
it, okay? Right? And if we're dealing with money, that's when you really have to now lock back into double spends and not sending the same, right? Because you can't have double spends, you can't have that.
Yeah, you have to be a lot
So
more critical.
that's why all these blockchains do have, like I said, we've got the account database. We're tracking what's going on in terms of, anyway, this stuff is here. So
Yeah.
when the nonce is changing,
From okay, yeah. Update the nonce.
perform basic accounting checks. If the nonce doesn't equal nonce plus 1, invalid transaction, wrong nonce. Right? And the thing about Ethereum, because it is decentralized, is this accounts database has to be also sunk up across all the different instances of Ethereum. You understand?
Yeah.
Like, because
So even though it has a database, it's still
it's
decentralized.
all decentralized. Every Ethereum will have a version of this, okay? Because as it's processing the blocks, it updates all the accounts that it knows about. So when an Ethereum system first comes up, it's got to get all the blocks. And as the blocks are coming in, it's updating, let's say, this accounting database for everything that's there. And then once it's in sync, it can start participating on the network, and it will know all your transactions and what nonce you're at and everything. So when the new block comes in, or when it starts trying to do this, right, the next one comes in, you can't spoof it because it's in sync. And this is when things like whole level of complexity starts to happen there, right?
Yeah.
And I've got a working reference model of this. Nothing you can put in production, but it freaking thing works, right?
Yeah.
With the ability to do both proof of work and sort of, I call it more, I don't call it proof of stake so much as proof of, not even authority. This is kind of cool, right? So on proof of work, somebody submits a block to the network. Everybody's trying to validate crunching numbers, right? Solving a problem. It's basically coming up with a number with a certain number of zeros in it based on, so you're hashing it. Hash, 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 hash. What is my zero count? What is my zero count? What is my zero count? Kevin, what do you got? Oh, I'm still doing it. Hey, guess what? I found a hash, right? Basically a nonce in a sense.
Yeah.
That if I keep changing this data, I finally get to it, I win. This is now what the new blockchain looks like.
Okay.
Right? That's the proof of work. It's 5,000 machines burning CPU all day, trying to change the data just a little bit so it finds a hash of n number of zeros. And that gets harder and harder. Everybody's complaining. So another thing that we did that Ethereum does now is it says, look, let's choose, imagine this problem. Okay, you got 5,000 people
Yep.
that each need to get a turn in submitting the next block to the network.
Yep.
Okay, so How do you choose who goes next this is a highly decentralized system, 5,000 computers.
Yeah.
Somebody has to go next. Everybody has to agree that that person goes next, and it has to be random.
Oh.
So you know how they do it?
How?
A high level, we do it here in this blockchain. We take a look at the last block.
Yeah.
Everybody has the last block.
Mm-hmm.
So everybody has that data. We run an algorithm that generates a number, say in our case, from 1 to 5,000.
Mm-hmm.
So we say, you're 1, I'm 2, Mohammed's 3, and every single node on this network gets a number from 1 to 5,000.
Got it.
We take the last block, we all run the same algorithm against that data, and it produces what? A number from 1 to 5,000. If that's your number, you go next. We don't know who that's going to be, though. It's random.
Yeah, it's
Then after the next block comes in, we all run it again. So this is one of these weird algorithms where it's random but predictable at the same time, as long as everybody's running the algorithm against the same data.
Yes.
So we do that in here too.
Okay, so everyone is gonna get the same output of that number. They're all gonna agree.
As long as we're all running the
On the
algorithm
same
against
data.
the same data, which everybody should, because the last block in the blockchain at some level should be.
Everybody agreed on it.
Oh, yeah.
Exactly.
How
Okay.
cool is that? So that's part of what Ethereum does today. And I'm telling you at a high level, there's intricacies, but essentially that's what they do today. And so this way, everybody essentially can get a turn to do the work without us burning the CPU on 5,000 machines.
Got it. Instead of everybody fighting, it's just kind of like, okay, we know this is the turn. Boom.
But
This is the
everybody
turn.
can
Boom.
figure it out on their own who goes next.
And that number can't repeat, or it can repeat.
It could, I guess, right? But now this is where math comes
That's
in
when it gets-
and all the other stuff, right? But at a high level, how cool is that?
Yeah.
We don't need any of this stuff because we're not doing that.
Mm-hmm.
Okay, but
That's how they do it at
I'm not
scale, though.
terribly worried about this one piece of data being reproducible, and somebody sending hello Kevin from me, because they won't be able to send. All anybody would ever be able to do if they were spoofing is send you duplicate messages of myself, right?
Yeah.
There's no real there's no money involved, none of that stuff. If there was, we would need an accounting database. We would need to sync that accounting database across all the caps, like Ethereum does. And I'd have to track your last nonce, and we'd have to use numbers. And if it wasn't the right nonce, I wouldn't allow your message to go through. But now we've got to create peer-to-peer networks, or we'd have to do it at least over NATs. And we don't need that right now.
Yeah, it's
Okay.
too much.
But you can start to imagine some of the this is good enough.
Mm-hmm.
Okay, for me, this is good enough. So every time that we send a piece of data, we'll do that nonce. And ideally, that means that the only spoofing would be the same message twice from somebody else.
Got it,
Right.
which doesn't really do anything.
It doesn't do anything. And the cap could internally track that. So we could keep at a cap level an in-memory, say, database of the nonces that you've used, right?
Mm-hmm.
We could make this an int and create a in-memory transient, right? Database of all your messages. And if we see a nonce that is the same or smaller, I wouldn't necessarily say larger ones would be fine, because you could be talking on another cap, right? But if we just made this an int, let's say we made it a int64, okay?
Mm-hmm.
And we did this. Just generate in our case, we just generate a random number. What we could add to this later is the same sort of accounting database. We don't sync it up.
Got it. It just stays. It's kind of
Keep
on the
it.
cap.
We keep it. Most clients are going to be on the same cap, and we just keep it in memory. We could on shutdown write it to disk and bring it back up. And if we see a nonce, we would only accept nonces that are larger than the last nonce. See, that would prevent spoofing on the same cap. And since most clients are staying on the same cap, that would be just as good without having to sync that across caps. So why don't we do that? We'll make the nonce a uint 64. It's a pretty damn big number, right? Don't need negative numbers.
No.
And right now we'll just make it an integer, right? And we'll write something to increment it. And then when we're done with all that, we'll add a little accounting database that tracks information about messages from these IDs. And then we can prevent somebody, because that would be the ultimate. Who cares if somebody found this message already? This cap already saw this nonce. So you can't send it again, right?
Yeah.
That gives us some better protection than the date.
This is cool stuff.
Now, you could still use a date and say that the date always, actually, you know what? Now that I think about it, we could use the date and just write down that says the date stamp, the date has to be within some scope of time, right? So it would always have to be something like now. It can never be in the future, right?
Yeah.
We agreed never in the future. Now, we're assuming that time is in sync across caps, which is a really hard thing to do. But we could have within some sort of scope, right? So can never be in the future. We can say can only be within, I mean, how slow is the network at this point, right? 10 seconds in the past. So if we did that, then we wouldn't need an accounting database with nonce numbers, because what we would say is this time would have to exist within 10 seconds of whatever the stamp is. So if the current time now is 12:37:30 and this message comes in at 10:37:20, okay, that's fine. That was sent within 10 seconds. We'll accept it. If it's not, we're going to assume that it's a bad actor.
Got it. Okay.
Right? And we can do that without having to maintain an accounting database. Right? You have to send a message. Now, network latency would be something. Clocks out of sync would be something. But we could say, hey, your machine has to be, all these machines are in sync anyway, right? Like, go to your terminal real quick and just type time at the same time. Ready? Write time. Don't hit enter yet.
Okay, wait.
Go. So mine said, it didn't give me the actual date time, did it? Oh, give me date. So do date. See, that's hit, yeah. So we don't even have it in seconds, right? I'm sure there's a way of getting it down to seconds there, and I've never played with this, but
R file name.
You think that's R seconds? I don't know. No, I don't know what that R file name seconds is. Oh, maybe it's minus I seconds. No, none of that works.
But they're,
yeah.
That's just giving you the day.
Oh, so do that. Date, all together, seconds, enter. So you can see like our two machines are pretty much in sync, right?
Yeah, it's identical.
And I think we could assume that everybody's going to be at enough of this sort of glare. So we could do the accounting database and track nonces at a cap level, but this might be a little bit more sort of universal.
Yeah.
And even 10 seconds might be way too much, right? But if we did the accounting database, it would be a much more accurate sort of system. So I think what we're going to do is we'll go with the idea of an accounting database at some point. and we'll store the nonces that we see, right? It has to be an increment. Like that's a guarantee that on that cap, nobody can spoof.
And it's at a cap level. It's at a cap.
It would
per
be at a cap level.
So it's still decentralized.
It's fine as long as it's just greater. We're not going to worry about it being the next one,
Got it.
because then we'd have to share our accounting database, and I think that's a little bit overkill. Again, most clients are going to be using the same
Same
cap anyway, right? So if I'm talking to you, it's usually going to be on my cap,
Got it.
right? If I don't see now, again, since the number could be greater than, it doesn't have to be the absolute next one. What would that mean? It would mean, it would have to be greater. So there's no way somebody can send the same message twice because they'd have to use the same nonce.
It'd have to be greater.
Yeah, it would have to be, right, it would have to be greater. But I don't know if that's any better than time lag, within like this message has a time to live sort of component to it. But the problem is that you could send the same message twice. In our case, you would try to use 2 again, and we would say, no,
Yeah.
you can't use 2. As opposed to on the other way, you could use the same time again, and we would accept it because it could still be within the same
That range or
glare.
Yeah.
So let's do this, and it will be fun to add that last little sort of piece to it anyway. So we have everything we need, right? Thanks to that signature package, we have everything we need. I'm going to save this work so far. Heck, signature. And thanks to the blockchain project, we've got all the sort of APIs we need. So we now know how to generate the private key.
Yep.
We know how to load it,
Yep.
which the client will use. We know how to figure out what our address is, right, our ID. And the client knows how, given a piece of data, how to sign it. We got to send this all over the wire. Not a big deal. It's go to go. So we can pull that off. And then on the cap side, we know how to, given a from address, right? I mean, given some data and the signature we'll send, we can get the ID. And then since we're going to put the from ID back into that message data, we'll be able to also validate it.
Got it. Okay.
Yeah. And now nobody can pretend to be somebody they're not, at least with the signature level.
Yeah.
And then once we get that working, we add a little accounting database for the nonce. We only allow a larger nonce. Then that's even better.
Yeah. That'll be solid.
Yeah. Yeah, you never know what cap you're going through is the thing there. So now the cap would track that, right? The cap would track it. I'm trying to think if we can do the nonce at a, you wouldn't know. I'm trying to think, can we do the nonce at a cap level, right?
The accounting, like accounting database. I don't know.
I mean, the client has to generate the client has to generate the nonce. There's no way around it. So I don't think we can do that. We'll see how it plays out. I think if you allow that or greater, again, nobody can send the same message twice. Somebody could send a message in the future, but the only way they could do that is they'd have to have your private key.
Yeah. Which no one should have.
No, and then you're insecure. But
Exactly.
I think this is better than the date stamp because I could send messages. I would still need your private key if the date stamp changed. But given the same data and the same stamp, I could allow the message to go twice, right?
Yeah.
So I'm trying to prevent the double message, right? This is the only way to sort of completely guarantee it. Again, there's no money involved, but you could get a sense of why we'd want to do that.
How it would work. Yeah.
Okay. There's no reason to do any more today. We'll end a little early. We always end late, but let's at least go back to our notes. So let's leave some notes for ourselves. So we have the hack program for identity, right? We understand how to use that now. So
Yep.
now we have to sort of implement the ID in the client and the cap, and that's going to require us to change some of the data structures and do some things. I don't think it's a huge lift. I think on Tuesday, I think for sure on Tuesday we can make that happen.
Got it.
And then we'll have sort of the rest of this. But then I'm going to add the account, right, DB, which is
Yes.
really in memory, right? And in memory, always like in memory. We could write it to disk to keep it, right? But how about we just call it the local account database, right? So when you shut down the server, we can write it to disk or so, like all these little files that we're creating,
Yeah.
right? And that will basically exist to be able to track the nonce values, just for extra security, right?
Yeah.
Yeah. All right. And then we've got all these other sort of things that we'll deal with. Might as well just clean this up here. So yeah, the AI agent's going to be kind of cool too once we get there. All right. And then some of that stuff is there. Okay, cool. So I kind of like this. It's not bad. I think it's got so much stuff here. It's eating up space. Let me just clean that up there. Oops. Okay. So I think on Tuesday, we'll definitely have, well, that one's done already. So we'll definitely have this done on Tuesday. We'll look at the clock at that point, and if we have time, I don't think this is going to take a long time to do once we have the other stuff in there. So then by the end of next week, we should have all this decentralized. Really, it's more decentralized identification, isn't it?
Yep.
Is really what it is. Not authentication as much as identification. But you've now seen how, let's just do that again, commit, update. And, you know, luckily all that work I did a couple years ago, we have all that sort of code there. But you can see I have no idea really how the algorithm works. But I know how to use the API.
Which is important for our purposes anyway.
Which is the only thing that really matters anyway. So, whew, not bad, bro. We got what we need. That's code that you can go back and study a little bit anyway.
Exactly.
On that. It's also Ethereum friendly. Though we're using our own Ardan IDs. And we could even, we wanted to get rid of the Ardan stuff and put the Ethereum stuff in there. And then any client library could just sort of work with it without the hack that we did. Maybe we should do that. Right?
Yeah.
It doesn't have to be Ardan ID. We could keep the Ethereum numbers and the Ethereum thing. Let me just add that because I'm going to forget for a second.
So we'll change it so that it uses Ethereum and it'll make it more.
It will just make it easier, right? So we'll
open source stuff.
So yeah, so use the Ethereum IDs and stamp. We do that, then if somebody wants to play with the JavaScript side, they don't have to do anything different. Like they don't have to do what I showed you. They can just use the Ethereum directly, and we talk as if we're an Ethereum node.
Got it.
Which is not a big deal, dude. It's just a matter of instead of this being 29, this is 27, and instead of Ardan ID, ETH ID, right? Right, they use 27, so we need that. And then down here, let's look this up real quick. This is the Ethereum stamp signature. I think it's the same. I think it's just, what am I doing there? I think it's called, let me find ours first. Because if I look it up this way, yeah. So if I say Ethereum signed message, somebody will. I'm just double checking that it's X19 there and not
X19 Ethereum signed message.
There it is, right there. Yeah.
At the very bottom.
See that? So if we make this Ethereum, see how Bitcoin does
18.
18, Ethereum's using 19 with the same sort of length.
Mm-hmm.
I don't know what the 19 means though.
Indicates a single byte value 25.
It's just some prefix for some sort of signed data, so it doesn't mean anything really.
Yeah, okay.
But if I do that, we'll make sure everything works. But if I do that, then you could use the Java, the Ethereum package out of the box. You don't have to change anything. It will just work, right? And that's pretty cool. So that would mean to me just that I can, the hack should still work. And it does. Okay. Okay, using ETH stamping values, right? And that's probably better because then when we come back here, right, and you saw that I had to
Do all of that.
do that, you wouldn't have to do this anymore. No. You could just literally get the latest release of ethers.js and essentially use the API exactly sort of the way I'm using it here. The one crazy thing with Go is that on the JavaScript side, Stringify puts these extra quotes around the RS, and Go doesn't know how to deal with that on the JSON side. We won't have that because we're doing JSON to JSON marshalling. But when we have to stringify the block, these big ints, you see here, it says replace this, find this and get rid of that quote.
Yeah.
Because Go doesn't put quotes around the numbers, but JavaScript does. So this is like this file is going to be important for anybody that wants to try to do this in JavaScript, because the only way to get the JSON marshalling to work on the Go side is to send these big ints as numbers, not as a string. And I couldn't find a way to get Stringify to not put quotes around this stuff, and the timestamp too. So shitty little hack there. But everything else would work just perfectly out of the box, right? And I know you already, you're thinking JavaScript client.
Yeah.
So by doing that, we're now 100% fully compliant with Ethereum.
Very cool.
Yeah. Dude, I spent God knows how many weeks, months putting all this together, right? But
there's a lot there.
There is. So you should take some time before we meet again next week to sort of look at it a little bit more. But I think I get a good sense from you that you do understand.
No, yeah, it makes a lot of sense, especially when doing the diagram to picture it. That helps.
Yeah, this is the key here. It's all about signing and getting the ID back. The math, the people that came up with this math is, you could say a lot of bad things about blockchain, and people have used it for scams. But over the last 10 years, our understanding of math as it relates to cryptography and these algorithms have grown exponentially.
To think about just the people who are creating that is another level.
No, it's another level.
Like, you can understand it now that we've had it. You can understand the high level of it, but low level, it's...
I mean, you can look at the code. It's all open source, but the math is let's come up with some math. We generate a private key and a public key.
Yeah.
And we could do all these crazy things with
Yeah.
I'm like, you're high as a kite, dude. But thank you. But without it, you wouldn't have the encryptions, and you wouldn't have this identification and all this sort of stuff. So it's really, really cool. right?
Yeah.
When you think about it, how do we get somebody to identify who I am without being able to send them the public key? Boom. Let's generate a signature that can be basically reversed engineered for a given set of data.
Exactly.
On the other
That's
side.
essentially what we're doing.
That's what that does.
That's essentially what.
Yeah, it's crazy.
That's
But now you can start to see the application of that. But without the nonce, it's all really insecure, isn't it?
exactly the nonce is like, to me in my head, the nonce is what's holding it all together. Because
Yes.
if not, it's a pattern. You can.
Yes, then it's all hackable. The nonce is key, and guaranteeing that somebody doesn't use the same nonce twice, like we're going to do with our little accounting database,
Yeah.
right? Like the date time would have worked, but there was still a glare of area where whatever that glare was, 5 seconds, where somebody could send the same thing twice.
Mm-hmm.
Again, we're not dealing with money. If we're dealing with money, it would be bad, right? Because you just sent me $100 and now I do it as fast as I can.
You can do it a bunch
Right.
of times.
So I think it's worth having the account database, even if it's just local.
Yeah.
It will work good enough for what we're doing.
It would be cool to see it too, to see how that kind of works. It's insane to me how the nonce is like, all this is all complicated stuff and algorithms and whatever, and then the nonce is just a simple increment, and that's basically what holds it all together. It's just
It keeps it secure.
an increment.
Yeah, that
that's
one
it.
integer keeps it secure.
Yeah.
Yeah. So now you'll see the word nonce everywhere.
Yes. Yes. I've never heard that until today.
Now you'll see it everywhere. All right, everybody. So we are pretty much done for today. We'll be back on Tuesday where we get this implemented, and then we'll all have our new sort of IDs. Remember that we changed the location of a bunch of stuff. So if you pull this down, you're going to have to, I should just show that one more time before we completely end. Remember, we moved under Zarf this, so just look real tight again. We moved cap, IDs under cap, though we didn't run any of this today, did we? We moved our contacts under client, config, and eventually everybody will have one of these keys when it's all said and done next week. So, yeah. Oop, so there we are. All right, finishing this off. Appreciate everybody that hung out with us. And next week, Tuesday, is going to be an exciting day when we've got distributed identity.
Mm-hmm.
Yeah. All right, bye.